You've probably heard of binary numbers, but did you know that 0.1 plus 0.2 doesn't equal 0.3 on your computer? Let me show you why, and how computers actually deal with decimal fractions. I will teach you how rational numbers are stored in computers, and tell you what their limitations are. Hey, my name is Oliver, and I am a final year bachelor's student. When I first started learning about computer science, floating point numbers completely confused me. Why couldn't computers just store the numbers directly? The jump from whole numbers to fractions did not make much sense to me. But now that I understand it, I want to show you what I wish I knew back then. If you are not yet familiar with binary numbers, I suggest you take a look at my playlist on binary numbers to get started. Watching those will make it much easier to grasp how rational numbers work in binary. To start off, I want to introduce a concept which you might be familiar with, called scientific notation. Scientific notation is used to represent very large or very small numbers in a way which is more easily interpretable. So, for example, if we have the number 1,330,000, this number has a lot of zeros, which will make the number take up more space on a page. And we can condense this format by shifting the decimal point, which would be here at the end. So, writing, for example, 133 and then multiplying it by 10 to the power of 4. And this 4 tells us that we need to move this decimal point 4 places to the right to get the number which we have. So in this case, it would be moving it from here 1, 2, 3, 4 points to the right. And this way we don't have to write all these zeros, or rather all these zeros, but can summarize this using only this component, so the 10 to the 4. This can also be written another way, for example 1.33 times 10 to the 6. And this is usually done with numbers, as I mentioned, that are very large or very small. For example, the masses of planets, or the weights of electrons and protons. This would also work in the other direction as I've described with small numbers. So if we have the number 0.00045, this can also be written as 45 times 10 to the, and then we would see how far we would move this decimal point to the right. So 1, 2, 3, 4, 5, 6. And this time we're moving to the left. So we would use the negative number. So -6. The same thing we can now do in binary. So we've used decimal until now, which uses the base 10. And you can see we have 10s here in the representation. And for binary, as might be familiar from one of the previous videos, we have our base equaling to 2. So we're moving from base equals to 10 to base equals 2. So in our representation, this number would now be a 2. And I will write the general representation and then explain it. So here we have the general representation, where we have an m times b to the power of e. In this case, for example, 45 would be this m, 10 would be this b, and -6 would be this e. Now these components have specific names. M being called the mantissa, b, as we're familiar with, the base, and lastly e, the exponent. And with these three numbers, we can represent any number. So this scientific notation works for any number, and the same is also true for the base being equal to 2. So the same way that using binary numbers we can represent any whole number, we can also represent every rational number using binary. Actually, we'd be able to represent any number if we had enough space. But since some numbers require an infinite amount of space, these are not representable. And usually there are a wide range of numbers that are not representable. This is also the reason why we have some inaccuracies in calculations. As I've described before, this exponent makes this decimal number float. And this is also why these numbers are called floats. They're called floating point numbers because we have the point that floats around based on the exponent. In our example of binary numbers, we also need to consider that we only have ones and zeros to represent this m. So this mantissa cannot, as before, use the digits 4 and 5. So a binary float could, for example, take this form, and this would actually just mean that this decimal gets moved 2 places here, and we have the number 101, and this is just our 5. But if, for example, we had a 1 here instead, we would get the number 10.1 in decimal, and this has another definition. Now that we have these 3 components, we know how to represent this number. We need to represent these 3 components, and this will be enough to store our number. But actually, we only need to store 2 because this base on computers will always be 2. So we only need to store this mantissa and this exponent for our number. We know how to represent whole numbers, and the mantissa and exponent both are whole numbers. So we can represent this in the way that we've learned before. One thing that is commonly done is to not use the 2's complement format for the mantissa, but only represent positive numbers, and then to add an extra bit for representing whether the number is positive or negative. So we would have this sign bit, and it would define whether we have a plus or minus here, commonly written as -1 to the power of s, with s only being able to be 1 or 0. The exponent is usually written in a format that is called excess. So the representation would usually be e is equal to e minus a bias, which is usually a large number. This will allow us to represent only this e, so still to represent it using only positive binary numbers, but the small e will then also be able to go down to -b. So we are representing these negative numbers, but not in our code, or rather in the representation itself, but rather through this assumption or this definition of it being defined by a subtraction. Now let us take a look at how specifically a number would be stored on the computer. So to decipher what exactly a number of bits represents as a floating number, we need to know which standard it uses. In this case, we're looking at the IEEE 754 standard. This defines how many bits are for the sign, the exponent, and the mantissa. Specifically, the sign will always have 1 bit because there's only plus and minus. But we do have different ways of distributing the bits for the mantissa and the exponent. Here, for example, we have the float 32, and this is a float represented by 32 bits. In the IEEE 754 standard, we give 8 bits to the exponent and 23 bits to the mantissa. You notice that the mantissa receives a lot more bits than the exponent. And this is because the mantissa usually stores the most information. It stores how many digits or which digits come after the comma. And if we had, say, only 1 bit for the mantissa, we would only be able to represent 1 or 2 digits, even if they can be extremely large or extremely small, thanks to this exponent. But usually we're more interested in the different digits that are in a number. So for example, we care more about representing a number like 1.23456 times 10 to the power of 6 than we care about representing a number like 1.2 times 10 to the power of 60. We usually don't work with such large numbers, and if we do work with such large numbers, it's also important to consider more digits after or before. So this format is usually seen as more useful. But of course, it also depends on the specific use case. And for this reason, we do have different standards. But again, this is the specific distribution of bits, and this is a more common standard for floating point numbers. Another important thing for the standard is what edge cases there are. So for example, usually we assume a leading 1 bit. So this m, this mantissa, would usually be 1 and then dot m. And then we would only represent this m here, and this implicit one that would stop us from having several ways of representing the same number. So it would stop us from being able to write 0.1 times 2 to the 1 or equal to 1 times 2 to 0 equal to 0.01 times 2 to the 2. So all these represent the same number, and we don't want to do this because this would make the storage more inefficient. We want every number to have a unique representation so we can represent more numbers. But this representation technique has a unique issue, and that is that we don't have a direct way to represent the 0. If we do not use this leading one, this implicit one, or we have infinite many ways to represent 0, but with this leading one we have none. And so usually you would say something like, all right, we will take the smallest number representable and not represent it directly, but have an edge case. So say, yeah, if e is equal to negative b, which we've defined as the smallest e, then we will just say that this number is 0. And the same is also done for infinity. So, for example, if e is max, so the maximum exponent, then we want to represent infinite. And depending on the sign, so whether it's plus or minus, we would have plus infinity and negative infinity. And you would also do this for null. So null or not a number, which represents usually some error in the computation. Like, for example, if a number is divided by 0. And this gives a hint that something went wrong and that this number is not what it's expected to be. That's important for catching errors. And yeah, there are a lot of exceptions that you can consider, and these are also dependent on the specific standard you use. Now, as I've mentioned before, you have the issue that certain computations don't really work. So, for example, 0.1 plus 0.2 is not equal to 0.3. And this is an issue of that you have a certain error when you add two different floating point numbers. So here, these mantissas, they offer a certain accuracy, but they're also not perfect. So even just storing a number already adds an error. And then if you add two of these mantissas, so if you add two floating point numbers to each other, there is an additional error because perhaps in the representation, the output will have some bit here or some bit out here, or it would require one. But this would then be lost when being stored in this format again. And this leads to these errors. And you can have differently critical errors. For example, adding floating point numbers has an error which is similar to multiplication and division. And these errors for addition, multiplication, and division, these can be limited, or rather, you know what the upper boundary is. You know that the error is always smaller than some value. But for subtractions, this is not the case. For subtractions, the errors are unbound. And now I'm specifically talking about the relative errors. But this is also a bit more advanced, and I might make a video on this in the future. However, the most important thing to remember is that a floating point number in binary can be represented similar to scientific notation using a mantissa, an exponent, and a sign. And combined, this representation looks like this, and different standards describe how the bits stored in a computer can be interpreted as the floating point number. So you've seen how computers work with rational numbers using floating point representation, and the limitations that this representation method has. So next time you deal with numbers in a program, remember, computers use base 2, not 10. Floating point have limits, some decimals just don't fit, and always be careful with precision. If you found this video helpful, you'll love my video on logic gates. It shows how computers start making decisions from just ones and zeros. I would also appreciate it if you liked the video and subscribe for more computer science content, and drop a comment with an idea of what you would like to see next. Thank you for watching.